This video compares Jordan form and Schur decomposition on one tiny perturbation. The point is not that Jordan form is false. The point is that it can be a terrible numerical witness. Start with a single 2 by 2 Jordan block. Then change only the lower left entry by epsilon. If epsilon is small, the matrix barely moved. Write delta equals square root of epsilon. It keeps the computation short, which is the least mathematics can do after creating this mess. For epsilon equals 0, the Jordan form has a 1 in the off-diagonal Jordan position. For every positive epsilon, the Jordan form is diagonal. So an arbitrarily tiny perturbation makes that Jordan entry jump from 1 to 0. Canonical forms are beautiful. They are also drama queens. The characteristic polynomial gives eigenvalues 1 plus delta and 1 minus delta. So positive epsilon gives 2 eigenvalues. Corresponding eigenvectors are v plus equals 1, delta, and v minus equals 1, negative delta. As delta goes to 0, these two eigenvectors both point toward the same vector. In plane geometry, the eigenbasis is almost collapsing. Their normalized dot product goes to 1, so the angle between them goes to 0. This is not a healthy basis. It is two nearly identical directions pretending to be coordinates. Put the eigenvectors into the columns of v delta. Because the columns are almost parallel, v delta squashes some non-small coefficient vectors into tiny geometric vectors. For example, the coefficient vector 1, negative 1 gets sent to 0, 2 delta. That vector becomes tiny when delta is tiny. Therefore the inverse change of coordinates must expand that tiny vector back to 1. Negative 1. That is the actual problem, not merely a scary-looking entry. Here is the exact decomposition. Since epsilon is positive, this is diagonal, so it is also the Jordan form. The inverse contains 1 over 2 delta because the eigenbasis is almost collapsed. The formula did not make the problem. It revealed the problem. Schur uses the normalized eigenvector as the first basis vector, then chooses a perpendicular second vector. So Q delta is orthonormal. The cost is that the middle matrix T delta is upper triangular instead of diagonal. That is not a bug. That is the entire strategy. A direct multiplication gives a epsilon equals Q delta, T delta, Q delta star. No nearly parallel basis is required. Here is the clean difference. As delta goes to 0, Q delta goes to the identity, and T delta goes right back to the original Jordan block. Jordan form tells a discontinuous-looking story. Diagonal for every positive epsilon. One Jordan block at epsilon equals 0. Schur tells a smoother story and keeps stable coordinates. How suspiciously useful. So the lesson is not that Jordan form is useless. It is excellent for exact structure. But it is fragile near defective matrices. Schur decomposition does not chase diagonal form at all costs. It keeps the basis orthonormal and accepts an upper triangular matrix. That is the trade. Less vanity, more survival. Next, we go back to positive operators, where square roots start building new inner products and new geometry. Finally, a constructive use of all this machinery.